linked lists, binary trees, graphs. In your journey through a computer science college education, chances are you're going to have to implement these data structures at one point of time or another. Today, we're going to take a look at a method to do this in Java using object-oriented programming, or OOP for short. When we do things this way, it makes the code very clean, very easy to read. And yeah, the cool thing about this is because all these data structures are node-based, which is something I'll explain in greater detail later on, you can extend this to build many types of data structures. So this is certainly a very good skill to have, and this is a great chance for you to practice your OOP. So let's fire up our Java IDEs and let's give this a try. You're watching another Random Wednesday episode on 0612 TV. Hello and welcome back to another Random Wednesday episode. Now, here's the deal. The couple of data structures I mentioned in the intro all have one thing in common, and that is the concept of having a node that connects to one or more other nodes, and sort of the connections just go from there, right? So you have things connected to more things, connected to more things. And basically, we want to capture this essence. With this kind of picture in mind, basically we can build a very generic node object, just an object representing one of these things, and then we give it the ability to chain to another node. Of course, when one node can chain to another node, you can, go ahead and chain as many nodes as you want together, and that's how you build your data structure. So this is very basic, very fundamental, and yet applicable in so many different data structures. So yeah, like I said, I think this is a, pretty good skill to have. Now, I'm not saying this is an efficient data structure by any stretch of the imagination. OOP in and of itself, requires quite a lot of things happening under the hood. So you will lose some performance benefits in this regard. However, one of the big things when it comes to, say, software engineering is that you want nice readable code. And this approach can definitely achieve that. But yeah, I think that's more or less enough talking, right? Let's go ahead and take a look at sort of a little contents page of what we're going to do today. And yeah, the rest of the episode will be putting that plan into action. So today's episode will be broken down into these 5 parts. We'll begin by building, just the simplest node. And in fact, this is enough for you to, take away the main thing I want to show you today. And that is to build a single node that helps you connect to other nodes. And of course, through that, you can build your data structure. Now, to apply our nodes and to see it in action, we'll be building a very simple linked list. Just to show you kind of a real-world application, so to speak. At this point, we have a very simple node that we can then extend and add more functionality to. So we're going to start by using generics to do this, allowing us to store information of any type on our nodes. Then what we're going to do is we're going to significantly increase the power of a particular node by allowing it to connect to any number of other nodes. So we just need to tweak our data structure very slightly, and you'll see that that can happen. To prove that it works correctly, we will be building just a simple graph data structure using our nodes, and we will run a simple graph algorithm on it to see this all work. And that will be our agenda for today. 5 parts. If you want to skip ahead to any part, you can pop open the video description, you will find timestamps there. With that said, let us begin with our episode. So before we go into building our node data structure, it will be good to see sort of what's going to be in it. Well, as it turns out, it's really simple. It's just going to hold a piece of data, which we're going to fix as an integer at the very beginning. And interestingly, it will also hold a node. That is our next node, right? And if this seems strange to you, good, that means you're thinking. In our next slide, we'll explain why this is okay. Of course, we will have some getters and setters to, change up these values, as well as a constructor. So, there is a bit of weirdness here because it seems like we are recursively containing a node within a node, right? So how does that work? As it turns out, Java holds references, not actual values, within their variables. What this means is, say we create a new node like this, right? We call it X. X does not contain the node itself. Instead, it simply holds a memory location. telling us where to find the actual node. While this part may seem obvious, it is what helps this entire data structure work. Because of course, if we were to have, well, a node storing another node, we will start to have this sort of phenomena where we have a node in a node in a node, and you don't want that. But luckily, that is not what happens. That is not what Java does. Instead, this could be more accurately represented with a picture like this. Each node is going to hold its own value, and it's going to have a reference to the next value. All it's going to tell us is where to find the next item. So this hangs together nicely if you want to have a data structure like a linked list, which is in fact what you're seeing here. This method is ideal. With this picture in mind, let us go ahead and build our basic node data structure. Alright, so let us begin, let us jump straight into this. I already have a file called node.java, so yeah, I'm going to start building my actual class, also called node, Don't forget the names have to be the same. As we've seen earlier, we're going to have two private values, one to hold the data and another to hold the next node, like so. So these are the only two pieces of information we are going to need. Then we're going to build our constructor, and for our constructor we're going to take in both pieces of information. So we'll start with our data and then our node. Within our constructor, we will simply assign these values. Now the user is able to construct the node and supply the two pieces of information that will go and be stored here. So the next thing we can move on to is to actually build our setters and getters. Let's start with our getters. Let's say we want to get the data, so public integer get data, and all we have to do is to return the data. Now, having everything in one line like this is not good in terms of style, but I'm trying to, make good use of the space here, so don't mind me. Well, let's do the get next one, We simply return our next node. So these are our getters. Our setters are fairly simple to build as well. All we have to do is to say set, We take in the value from the user like so, and we simply assign it to our field. So we're going to do the same again for our next node, set next, and we'll set our next to our next node. So in fact, this is it, This is a very simple data structure. We are able to hold and manipulate a piece of data. We are also able to hold and manipulate another node, which in fact tells us where the next item actually is. So yeah, with this, we are ready to go ahead and apply it, to try it out. Before we use our linked list to do it, let us just do a very simple primitive test first. And how we're going to do it is we're going to just create something that can be run right within our node class. So we're going to go public static void main, That's how Java programs start. And we're going to just create our node object like so. So let's say it has the value 1, and it doesn't link to anything just yet. Now, if we were to compile this should run, we should not get any errors. Of course, we also don't get any output, So not just yet. What we're going to have to do now is we're going to have to try and say x.getData, for example, and we're going to print that out. So system.out.println, like so. So we're going to try and get the information from our node and print it out. So far, so good. What we can then do is we can create a new node called y that now links to node x. So what we can now do is very interesting because, of course, we can get the data out of y. We should see 2 in this case, which we do. But we can also now use get next to get our next node. So this basically means the same thing as x, If this worked correctly, this and this would be equivalent. So if this was x, we should be able to run get data on it. And again, if this was x, we would see the data 1. So let's go ahead and compile this and see, and there you go, we have our 1. So this is how you basically have nodes, link them together, and traverse through them. So as promised, let's test this out with a linked list. But as mentioned, I've already done a full episode on linked lists in the past, right? And if you want to see that, the episode is up here, right? You can click on the card that appears. Over here, I'm not going to go too much into detail. I'm just going to very quickly show you some operations we can do on our linked list and what sort of, pointer manipulations that entails. So firstly, a linked list is essentially a bunch of nodes chained together. It's a data structure that, works like an array, except it's not bounded by any length. You can add things, you can remove things from the middle of the list, right? Whatever you like. You're not quite as bounded as with an array. A linked list only needs to maintain a head, that is, a link to the very first item in the chain. Because each item links to each other, being able to find the first item means you will be able to eventually access any item within the list, right? And how you do that is you start from the head. Let's say I want to find the third item. Well, I just need to traverse forward twice, and I find it there. In fact, let's look at the code for finding. I have the other functions written as well, but we'll skip over those. Essentially, to find something, we need to maintain a current node. And this tells us sort of where we are within the list at that point. To move forwards, we simply update that current node by setting it to the next one. How this works is this. We have our currents pointing to the head at the very beginning, and if we were to say current.getNext, that means this next node, right? And if we were to assign current to this, that moves that forward. In the next iteration, when we say current.getNext, we are now referring to the next item. And by doing this repeatedly in a loop, we can start to basically traverse forwards. So yeah, that is sort of the core idea. Of course, traversal, right, just reading back isn't so fun. We can also do insertion. Say we want to insert a new item here, we will have to do 2 pointer manipulations, like so. The previous item must point to the new item. The new item must point to the item that is currently at that position. If we were to straighten the whole thing out, you will see that indeed the new item replaces the position of the old item, and everything else just moves forwards. Another thing we can do is deletion. Let's say we want to get rid of this guy. Well, all we have to do is to redirect the node before it to the node after it, like so. Since we have now basically sort of skipped past this item, right, when we traverse along, we'll just skip it over. And effectively, it becomes no longer a part of the list. And yeah, when Java does its garbage collection, that is going to get removed. So I've collapsed away some of the code here, right? And essentially, this is our whole linked list class. In this class, I have the functions find, insert, delete, and toString, which allows us to visualize the entire list at once. And yeah, I have a main function here that basically allows us to, exercise all of these functions. I start by creating a new linked list. I insert 2 values in there, both inserting at the head. And what that means is, this item number 2 should now get pushed forwards. We print it out using our find function. And yeah, our results show us that indeed our second item now says 2. So yeah, we do several more insertion operations, including one that is not at the head, and that gives us this result. We've basically inserted item 5 at position 1. Finally, we also do a deletion, and yeah, as you can see, it all works exactly as you would expect. So again, I know I'm being quite vague about what the linked list itself is doing. That's because I don't want to spend too much time here. This episode is about the nodes, not linked lists. But again, this piece of code will be available for download in the video description. In fact, if I have the time to write up a blog post on linked lists, right, you will be able to refer to that as well, in addition to the video. So no worries, right? We have this content available. Right now, the main thing we're seeing is how we can use our node to implement a more complex data structure. So we now have our node, right, and we can now chain them together in our main function to create a linked list. Now, at present moment, our linked list is still quite limited because it only holds integers. So what we're going to do is we're going to use a Java function called generics. And what this is going to give us is the ability to basically add any kind of information to our class. And all we need is just a couple of small tweaks. So let's see how this is done. So let's come back to our node class to see how we can implement the concept of generics. Here's how we do it. After the class name, we'll insert our angle brackets. And the idea is, within this bracket, the user is going to give us some data type. Of course, at this point is unknown to us, so we can call it something like t. And the idea is t is like a variable, except in this case, what it represents is not a value, but a data type. So what this means is this node will be handling items, right, data of the type t. Of course, if that's the case, we're going to have to change up the type of our data here. We're going to have to change up what is actually passed in by the user. We're also going to have to change our getter and our setter. So with this in mind, you see that we have no more references to integer at all. So yeah, everything here is now with regard to the unknown type t. Now let's go back to our main function. It was commented out. I'm going to go ahead and put it back. In this function, we have basically created two nodes, right? And we assume that the type was integer. Of course, that's no longer the case, right? We're going to go ahead and, well, specify the type now. And let's say we want strings of text. So we say string over here like so. Of course, we have to repeat this for each reference to the node class like so. And of course, we have to change the values here as well. Let's go ahead and have a hello here and a world here, right? Our two strings. And then let's go ahead and print out both. Right? So we start by printing out the value of y.getData. And then we're gonna again traverse to the next one, which is our x, and then get the data again. Compiling this, well, we get our results, world and hello. Well, it happens to be in that order because that's the order we've created these two values. But as you can see, by using generics, we are now able to represent any type of data, including strings of text. So yeah, that has been generics. Hopefully it's not too weird. I know the syntax is a little bit strange at the beginning. It's just an unknown data type, kind of like a variable. Now, with this idea in mind, we can start to generalize things a little bit. This is where things start to get a little bit more complex because different data structures will allow different kinds of linkages. For example, a doubly linked list will allow you to link back to the previous element instead of just, continuously going forwards. Instead of doing that, however, we're going to go completely general, and that is a node can now link to any number of other nodes. In order to do this, several pretty big changes will have to be done to our node class. For one, we no longer hold a single next element. We now need to hold, well, potentially 0 or more. In order to do this, we're going to enlist the help of one of Java's inbuilt classes, namely the ArrayList class. So in order to use this, we're going to go ahead and import the ArrayList class itself, and we're going to replace our node. So now, instead of a single node, we want an array list of nodes instead. We're going to call this neighbors. Of course, our constructor and all our functions are also going to have to change in order to reflect this. First, let's actually just drop the whole neighbor from our constructor, right? We're not going to care about that. Of course, since we now have this array list object, we're going to have to initialize it properly. So let's go ahead and basically construct our array list object, like so. The whole concept of getNext and setNext over here no longer applies, so we're going to get rid of those as well. Of course, the data doesn't change, right? We already have our broad generic data, which is great. But now we need to think of some way to get and set our neighbors. Let's do get first. What I'm going to do is I'm going to create a new function, public. And since now we're not only getting back one node, right? We have a whole bunch of nodes. So we're going to return an array of nodes. What we're going to return is we're going to return our neighbors object, and we're going to convert it to an array. So this one is pretty interesting, right? The syntax is fairly strange as well. Java wants us to basically pass in an array to tell it what data type to actually return. So yeah, we're just doing this to fit how the toArray function works. To get the neighbors, right, we take our array list, convert it to an actual array, and give that back to the user. So that's one. Now we have to also be able to set the neighbors. So all I'm going to do is I'm going to write a very simple function here that takes in an array and simply sets all the values into our array list. So let's go with public void set neighbors, and of course we now need to pass in an array of neighbors. We will want to loop through this, right? So for, we're going to use a looping variable called I, and yeah, basically just loop through the entire array. For each item we encounter, we're going to go ahead and add that to our neighbors array list, right? So we want to read out that value from the list like so. Now, clearly, these two methods are not the simplest way of expressing yourselves. So if you're writing this yourself, you will probably want more getters and setters to either search or modify individual neighbors instead of dealing with the whole lot at once, like what I'm doing here. But well, I want to keep it simple, I don't want it too complex, so we're gonna leave it as it is. What we have now is a node that links to an arbitrary number of other nodes. And what this allows us to do is to express very complex ideas such as graphs. In fact, what we can try to do now is to express a graph. In fact, something like this. So this is just a very simple graph, right? Just a couple of nodes, no directions, no edge weights, right? We're keeping it simple here. Our goal is to basically express this in terms of our node objects, as we've seen earlier. So I've already gone ahead and built the code, right? And it looks something like this. You can ignore the other stuff first, right? We're going to do depth first search on this later on. But let's just focus our attention on these 12 lines first. This part should be nothing new to you. We're just creating a whole bunch of nodes, right? And they're containing the strings A through to F. Also, we're giving them variable names that happen to also be A through to F, right? Like I said, I'm keeping it simple. This part is the more interesting part, because what we're doing is we're going to assign the neighbors of every single node. So we're going to start with node A. We want to set its neighbors to this array of nodes, right? So B, C, and D here are variable names referring to these three objects in particular. So because of the way our set neighbors function works, right, it takes in just an array of nodes, we can quite easily package our linkages like this. Indeed, all we're representing are these three connections between A and B, C, and D. If we move on to look at B, you'll realize that, well, the neighbors of B include A. So yeah, this is an interesting consideration that you must remember. Because all the edges of this graph have no specific direction, what this means is you can treat every single one of these edges as bidirectional. A can go to B, B can go to A, right? And that is why we need to actually, state this, right? It seems to be stating something twice, but there is some significance in expressing things this way because, well, it is a bidirectional relationship. With just these 12 lines, we're able to represent that entire graph I've just shown you. Of course, just having a graph isn't all that fun, right? Let's actually do some simple graph algorithms on this. The algorithm of choice is depth first search. Now, here's how depth first search works. The idea is we want to visit every single node exactly once. We want to start at a particular node and just go as far as we can until we basically cannot go anymore. Then we'll kind of retrace our steps, right? And then try and find another path, going down again as far as we possibly can. You will trace out a different path depending on what node you start out at. So yeah, let's basically try this out and see how this goes. Here's our code for depth first search. I will not go into detail on what we're doing here, right? If you want to find out more about depth first search, we have already done a video about this. Basically, this is the entire algorithm, right? It uses a stack and an array list, which is why at the top of this page, I've actually imported both. Then at the end, what I've done is I've run depth first search starting from B, right? So that will give me one set of values. And then again on D, which will give me yet another different answer. So yeah, let's go ahead and run this and we'll see that the answers that come back are as follows. Now, this isn't sort of super clear what's happening. So instead, let's actually read this out with our diagram. First, we ran depth first search on B. And what it gave us were the results BAC, DFE. So essentially, the path is actually traversed is B, A, C, D, F, like so. So basically it just went as deep as it possibly could. And yeah, we started at B and we traversed all the way down here to F. Since we can't go any further, we had to backtrack. At D, nowhere else to go, backtrack again. And from C, that is where we found E. So this gives us an interesting pattern like this. In fact, this is a tree called a spanning tree. Again, I'm not going to, go into too much detail about what that means. You can watch the graph algorithms playlist if you want to find out more. So, our second run started at D instead. And what this gave us were the results DAB, FCE. So, going back again to our diagram, let's try to see what we are seeing here. We start off at D, and what we get is A, B, F. Right, so that is one path that's traced down. Since we can't go any further, we're going to have to backtrack backwards all the way back to the very beginning. And then we will traverse to C and E respectively. So yeah, those are the paths that we have found. And notice how we get a very different spanning tree this time because we've started from a different node. Right, and in fact, depending on which node you start on, you will get a different spanning tree each time. So yeah, there you go. By just upgrading our node a little bit, we are now able to do a far more complex algorithm, namely depth-first search. Again, I don't want to spend too much time talking about these algorithms, right? They are sort of outside of the scope of what we're discussing here. But what I'm trying to show you is the power of our node class. By augmenting this, we're able to get more and more functionality out of this. And while we're going to end the episode with this version of the node class, you can easily take this further. For example, if you want weighted edges, you may want to add another array list that represents this information. If you want to add a bunch of flags, like a visited flag, well, you can do that here as well. So yeah, the idea is we now have a very broad generic node class that already does quite a couple of things, and yet leaves so much room for you to explore further. That's the power of object-oriented programming. If you want any of the code that has been shown in the episode, do pop open the video description and you will find a link there. It will go to the NERDfirst blog. I will have some write-up there as well as the download link. Anyway, that's all there is for this Random Wednesday episode. I hope you learned something today. Like I said, this is a very fundamental skill, right? You will probably want to sort of take the concepts you have gained here and sort of see how you can actually take it further. That's all there is for this episode. Thank you very much for watching, and until next time, you're watching 0612 TV with NERDfirst.net. Thank you very much for watching. If you like my work and are feeling generous, you can shoot me a one-time donation on PayPal or sign up for a recurring one on Patreon. Of course, you can simply like, comment, and subscribe. You know the deal. For more videos, links to my channel and a related playlist are on screen. Thank you for your support.